So my name is Michael Baudouin. I am professor at the University of Lille and researcher at IEMN Institute.
My name is Sarah Kleve and I'm a senior researcher here at the IEMN, who's associated to the University of Lille.
My name is Henrik Bruus and I am a professor at theoretical physics at the Technical University of Denmark.
So I will just briefly introduce the project. So imagine you were able to grab some objects, some micro objects very precisely in 3D and without even touching them. Then it will open many perspectives. For example, in medicine, where you could, do some microsurgery by moving some object inside the body, but without making incision of the body. And this is fundamental because if you do incision, you introduce germ and there can be some complications. Another point is you could also, if you were able to do this magic operation to grab some objects remotely in the body without touching them, you could also do some targeted drug delivery and bring some medicine exactly where you want to act. So in our team, we develop such magical tool by using acoustic waves. So basically we use sound to grab some objects in 3 dimensions and we use this vibration to manipulate these objects. So our team in Lille was the first to be able to perform very precise operation on cells and to be able to manipulate cells and organize them precisely. And then now we want to bring this idea of acoustical tweezers, this is their name, to the next level, and this is what my colleague will tell you now.
I'll briefly explain what our 3 axes are that we will be working on in the project ICMINA. My colleague has told you about the acoustic forces that we are working with, and in the first axis we are going to apply this to even smaller scales. That means right now we are able to work at micrometric level and then we are going down to nanometric level, which means on the physical side that we are going up to gigahertz acoustic tweezers, and this is the first one. In the second one, we'll combine acoustics with optics. We'll exploit the advantages of both of them. Optics are very versatile and you can easily shape the fields, and in the acoustics you can get strong forces. So this makes that together you'll make things operable with acoustics that are usually not, just by using acoustics en place. And in the third axis we'll be working on acoustically driven 3D microswimmers. That means this time we are not exploiting an acoustic wave in a special form, but it's rather the receiver, the swimmer, that is doing the job. And people have already been working on this, but the problem is 3D steerability. If, for instance, you want to have a microswimmer in a human body, you need to be able to steer it in a 3D way, and that's where people are failing. That's exactly what we are aiming to do by understanding the underlying physics and solving this problem from that way.
I'm quite excited about this project to collaborate with the University of Lille, with the teams of Michael Baudouin and Sarah Kleve, because we are trying to do something new in the field of acoustofluidics. And to do what we are aiming at, we need to combine our expertises, which in Lille is primarily the fantastic fabrication facilities they have and the experimental instrumentation they have. Whereas the expertise I bring in is on the theoretical side. We also plan in the project to have quite a good amount of student exchange between Lille and Copenhagen to provide the good progress in this project.